So in that case, so we are assuming that k has to be greater than or equal to 2. So for k greater than or equal to 2, then we will have fk is equal to what? Fk is equal to 1 over square root 5 times this one, square root 5 plus 1 over 2 to the power what? K plus 1, right? Minus 1 over square root 5 to the power 1 minus square root 5 over 2 to the power k plus 1. This is fk that we have. And then what? We want to show that it is equal to fk minus 1 plus fk minus 2. Okay, then what should we do? Difficult, right? If you look at this, how can I break it down into two parts? Perhaps a better way is, let's check it using, we call it the backward reasoning. Let's do it also on the other side and check whether these two are going to be the same. So let's also check fk minus 1 plus fk minus 2. Is that okay? So what is fk minus 1 plus fk minus 2? What is it? So we copy it. So let's copy it. So it is 1 over square root 5 what? 1 over square root 5 what? 1 over square root 5 times 1 square root 5 plus 1 over 2 k minus 1. So k minus 1 over square root 5, 1 minus square root 5 over 2 k plus 1 over square root 5, square root 5 plus 1 over 2 k minus 1. Is that okay? And then, yeah, not enough space. So let me write it down here. 1 over square root 5 times 1 minus square root 5 over 2 k minus 1. Is that okay? Is that okay? Now, let's look at this term and this term. So what's so special about them? So they can take out the factor 1 over square root 5 times square root 5 plus 1 over 2 to the power k minus 1. Am I correct? Is that okay? And then what is left? So you get square root 5 plus 1 over 2 and then plus 1, right? Right? Is that okay? So let me use the board. So the orange part. Okay, so this is the orange part. So if you look at the orange part, you can take out 1 over square root 5 times square root 5 plus 1 over 2 to the power k minus 1 outside. And then you get square root 5 plus 1 over 2 plus 1. Am I correct? And so we also have this green part. This green part is minus 1 over square root 5 times 1 minus square root 5 over 2 to the power k minus 1 times 1 minus square root 5 over 2 plus 1. Is it okay? Right? What's so special? This time, this part is this 1 plus 1. And then we recall that this is exactly equal to square root 5 plus 1 over 2 square. Is it? Yeah, because this is the root of x squared is equal to x plus 1. So this number has a special property that you square itself, it is equal to 1 plus itself. And similarly, for this one, this is equal to 1 minus square root 5 over 2 square. Okay? And then, so this has a, okay, done. You put it back. This k minus 1 becomes k plus 1. You put it back. This k minus 1 becomes k plus 1. And then we find that this is equal to, it turns out that it is equal to fk. Okay? So we just proved that this formula has the property that f0 is equal to 1, f1 is equal to 1, and then fk is equal to fk minus 1 plus fk minus 2. So it must be the same as the Fibonacci sequence. Is that okay? So why? So where is the strong induction? Where is the strong induction? So I'm claiming that this works. How can I suddenly say fk minus 1 is equal to this one? Fk minus 2 is equal to this one. I'm actually saying that all the numbers less than fk, so fk minus 1, fk minus 2 up to f1, all the Fibonacci number that is less than fk, they have agreed in this form. So in that sense, if we have fk minus 1 plus fk minus 2, we will then have the new Fibonacci number, fk, to be in the same form as we expect. So we are showing that fk minus 1 is correct and fk minus 2 is correct, then fk will be in the correct form. So it is more than the original induction format that we have. We have 2 implies 1, rather than one thing implies 1. Okay? Yeah. Okay, that's it. Let me see. Okay. Let me give you one more example. So induction is not that boring. Okay, it is not always proving mathematical formula. We can prove something is correct. We can prove a certain way of solving a problem is correct by using induction. So here, I'm going to introduce to you a way to sort numbers. So we are looking at a sorting problem. Sort. Sort means to arrange things in correct order. So let's say we have a bunch of cars. So there are a bunch of cars. Let's say there are n cars. All of them are written with a different number on it. And we want to arrange these cars from small to large. So how can we do? Okay, of course you can open the cars and then check which one is which by doing some arrangement. But here we allow you to only, okay, every time you can only select 2 cars. Maybe you are selecting this one and you are selecting this one. And then there is some other people who will tell you which one is larger, which one is smaller. Is that okay? So you can only know the result. You can pick 2 cars that you want, and you only know which one is larger, which one is smaller. Now, can you still sort these n cars? Yes, I will tell you yes. So first of all, make the problem a little bit simpler. Can you find the card with the smallest number? How can you get a card with the smallest number? So you pick the first card. You compare it with the second card and ask, which one is smaller? You keep the smaller one. You keep this card and compare it with the third card and ask which card is smaller, and then you will keep the smaller one. You do this again and again, and up to the last card. After these n-1 comparisons, you know which card is the smallest card. Is that okay? Okay, so just by using comparison, you can find the smallest. So this is the smallest. Now, once you have identified the smallest card, so there are only n-1 cards left. And you can repeat the procedure just by looking at these n-1 cards and get the smallest of these n-1 cards. So if you get the smallest of these cards, this will be the second smallest, and so on and so forth. So you can repeat this procedure and then find smallest card, and then the second smallest card, and then the third smallest card. And in that sense, you can sort the cards. So this problem is solvable. We can solve it. And then in the worst case, in the worst case, or in any case, using this algorithm, how many comparisons we are doing? We have n-1 comparison to get the smallest card, and then we have n-2 comparison to get the next smallest card, and so on and so forth. And up to the end, we have 1 card. We have 2 cards left, and then there is 1 comparison to get the smaller one. So these are the number of comparisons that we need. And this is roughly, okay, n squared divided by 2 comparisons. Is that okay? Roughly. Okay, now, so this algorithm is called, there is a name for this sorting method. This sorting method is called selection sort, because every time we are selecting the smallest card out. Selection sort. Okay. Now let me tell you another sorting algorithm. Okay. Okay. Okay, so I'll tell you another sorting algorithm. Its name is called Quicksort. So why is it called Quicksort? Because it is quick, on average, okay. But it is not quick in the worst case. So what is Quicksort? Quicksort is like this. So you still have n cards. So it does something more, okay, or similar. So there are n cards. You pick out one card. You pick any one card, and use this card to compare with every other card in this group. You compare with everyone. Now, after this comparison, you will know that some cards are smaller. Let's call this card X. I don't know the value of X, but I am going to use X to compare with everyone. So after compare X with everyone, I will know some cards are smaller than X. And then I will know that there are some cards larger than X. And then this is the card X itself. Is that okay? Okay. Now, after doing this procedure, what do I know? I know exactly how small X is. So let's say there are 5 numbers smaller than X, then X will be the 6th smallest number. Is that okay? If there are 10 numbers smaller than X, then that means that X will be the 11th smallest number. Is that okay? If there are no numbers smaller than X, then X will be the smallest number. So after comparing X with every other card, actually I know the relative order of X among all the numbers in these n cards. So the position of X is now fixed. And to get everything sorted, arranged from small to large, then what do we need to do? We need to make this part sorted, and we also make this part sorted. If we can arrange this part from small to large, then we write the small to large of this set of cards, and then X, and then arrange this part from small to large and write it here. Then we will have a complete sorted sequence from small to large. Is that okay? Okay, if you're okay with this, could you please raise your hand? Excellent. And then how do we do this part? So this is the definition of quicksort. Okay, so here what we need to do is we want to sort this part. Of course, you can use any method to sort this part. You can use selection sort to sort this part. But somehow, if you believe that this quicksort is nice, it's really nice, then we are going to use the same procedure. We are going to use quicksort to sort this part. And then we are applying quicksort to sort this part. So what is meant by applying quicksort to sort this part? It's simple. So it means that from this part, we select a card, and then use that card to compare with every other else. We get smaller, and then the smaller, larger part. Okay, the larger of the smaller part and the smaller of the smaller part. And then for each part, we use quicksort recursively. We use the same method to solve a smaller problem. So we call it recursion, recursively, to sort the smaller part. Is that okay? Okay, excellent. Okay, it looks correct, right? So in the end, when you have only 1 or 2 cards left, then it is easy. When you have just 1 card left, you don't need to sort. It is already in the correct order. When you have 2 cards left, then you just compare, and then you return the small and then large of that one. Okay, here we want to show quicksort is correct. So what is meant by correct? So here we are solving a sorting problem. So a correct output will mean that all the sorted cards, all the cards will be arranged from small to large. Then this is meant by correct. We are not talking about quicksort is quick, so we are not talking about this. Quicksort can be very slow, we will see. But at least quicksort is correct. So how can we show that quicksort is correct? So any algorithm that works, any recursive algorithm, any algorithm that is using recursion, you can always prove it by using induction. Okay. So recursion and induction are something very, very closely related. Recursion means that you are using the same trick to solve a smaller problem. Like the fireman, like the interview question, the mathematician goes to interview. I hope you still remember. If you have a small fire, how do you solve it? Okay, because the mathematician knows how to solve the problem when he sees a big fire. Okay, when he sees a big fire, then he calls the fire station. So when he solves the problem of you see a small fire, then he makes it what? He makes it larger. Yes, and then call the fire station. Okay, so when you see a problem, you make it to something that you are familiar, and then you solve it. The recursion idea is like this. When you see a problem, you can break it down into different problems. And for each problem, you try to solve it using the same method. So this is called recursion. Quicksort is like this. You have a big problem, you want to solve it. Let's define a method called quicksort. Quicksort is you fix a card and put it into two small parts. And then for each smaller part, you find that it is still the same type of problem. It is the same sorting problem. So we can apply quicksort to sort this part and to sort this part. Okay? So this is recursion. And then recursion is related to induction because recursion always solve a large problem into a small problem by solving smaller problem. So let's see how induction works. Okay. So induction works, first of all, we want to show that quicksort works for small size problems. So quicksort can sort one number correctly, right? Yeah, because we just say one number, we return the number. So it is sorted, it is correct. It also, okay, if you don't believe that it can solve small size problem, let's take a look of when there are two numbers to be sorted. Quicksort can sort two numbers correctly because it just makes one comparison and returns small and then large. Is that okay? Now, assume that, okay, we want to show quicksort always work for any other size problem. So we assume what? We assume that quicksort can solve a problem of size 1, size 2, size 3, up to size k minus 1. So assuming that if a problem has size 1, 2, 3 up to k minus 1, quicksort can do it correctly. Now, if you are given a problem of size k, then what will quicksort do? What will quicksort do? Quicksort will select a number from inside, compare this number with every other numbers, and then we get a smaller part, we get a larger part here. Is that okay? Now, originally, there are k numbers. So we are assuming that there are k numbers here. After you put out one card, you get a problem here and a problem here. The special thing is that for each of these problems, the size is less than k minus 1. The size is less than k minus 1. Okay. Now induction tells us that quicksort can do 1, 2, 3 up to k minus 1 properly. So quicksort can sort these smaller parts correctly. It can sort the larger parts correctly. Now, if the smaller part is sorted correctly and the larger part is sorted correctly, the combination of this one will be the sorted sequence that you want. Is that okay? Because all the numbers here are less than x, so they should be put before x and they are sorted. So it is like increasing, and then you have x. All the numbers here are larger than x, and then they are sorted, so it is further increasing like this. So that means that all the numbers in this will be, all the k numbers will then be sorted. And that's why quicksort is correct. Is that okay? Okay? Good. Nice. Okay. So quicksort is correct. But quicksort is slow in the worst case. Yeah, I forget it. So quicksort takes roughly n squared over 2 comparisons in the worst case. So in the worst case, in the worst case, quicksort will need n squared minus 2 comparison. So it is no better than selection sort. Why? Why in the worst case it will take n squared over 2 comparison? So you don't need to know what is the worst case. You just need to show that there exists some case which is not good, and it takes roughly n squared over 2. Then in the worst case it takes worse. Okay, worse. No, it's not worse. It takes worse. Okay, worse than n squared over 2 comparisons. So what could be bad for this one? So what could be good? So first of all, when will quicksort be good? When will quicksort be good? When will quicksort be good? So n squared over 2 comes from what? You have comparison between any pair of numbers. Then you have n squared over 2. This is how things will become worse, right? So if I have identified some x here that partitions the number into 2 groups, one is smaller and one is larger. So what is the benefit of doing this step? So what kind of comparisons we can avoid? So I have x here already, right? Okay. After this step, so at this step, only x is compared with every numbers here, right? But do you know that some numbers will never be compared anymore? Which numbers will not be compared? Largest, you mean the numbers here? Or the smallest? But okay.
You pick the largest.
Oh, okay, you pick x the largest, but then, okay, good point, but not the exact point. So first of all, once x is compared with every other number, then x will never be compared with any other number again, because x is now fixed, right? And then you focus on problems on small part and large part. But numbers in large part, will they be compared? So I have some numbers here. We cannot tell. They may be compared, they may be not. Numbers in the same group may still be compared. But numbers from different groups will never be compared. Can you see this? Okay? So once x is compared with everyone, then you save the comparison between the small group and the large group. Okay. The more that you save, the faster the algorithm, the fewer comparisons you need. So when will be a good case? When will be a bad case? To save operations, should we have a large group here, a small group here, or should we have both groups of equal size? Equal size, exactly. If both groups are of equal size, you are roughly, so equal size, you are saving how many? So let's say this is roughly n over 2 numbers here, this is n over 2 numbers here. You are roughly saving n squared over 4 comparisons. This is a lot. You have n squared over 2 in the worst case at the beginning, but you are saving half of it. So it is a good case. What is a bad case? A bad case is you do not save anything. So when is you do not save anything? You unfortunately pick x to be the largest number. So in that case, nothing here, 0. All the things here, so you save 0 comparison. So you are not saving anything. So that means that in the worst case, you pick x every time to be the largest or the smallest number. Then you don't save anything. And then up to the end, you still need n squared over 2 comparison. Okay? But if you can save a lot, okay, so let's say every time you save a lot, roughly half numbers here, roughly half of the numbers here, then this running time can be fast. It takes roughly n times log of n comparisons. And then you can see that, okay, there is a theorem, no comparison sort. No sorting algorithm that makes use of only comparison can be faster than n times log n. So quicksort is fast in the best case, very fast, optimal in the best case, and still worse, very slow in the worst case. Okay, but why do we call it quicksort? Why do we call it? It is because for most of the input, it is quick. You don't meet the worst case a lot. Okay, you don't meet the worst case a lot. For instance, okay, suppose that you find the x randomly. You find the x randomly. So there are n numbers here. So let's say the numbers are from 1, 3 up to n. If you find x to be in the middle range, So let's say this is n over 4 numbers here, n over 4 numbers here, and then there are n over 2 numbers here. So roughly, this is the middle range. If you find any of the numbers here, you are saving at least n squared over 16. Right? You're saving at least n squared over 16. N squared over 16 is a lot when you compare it with the worst case n squared over 2. So if every time you are finding a number that is in the middle range, the middle half, you are saving a lot. And then it is like the best case that you have. Okay? So if you are interested, then you may take a look of the analysis of Quicksort from the internet. Okay, that's it. Okay, so on Wednesday we will talk more, continue with some of the remaining examples of this mathematical induction. Okay, thanks.